effective at the end. I'll convince you later. Okay, so it's an error that is only effective on the unit of W's law that is incoherent, but then the error will be cancelled out by the next computation. Let's see, okay? For the other water content, W quick, I define it to 0. Okay, that's fine. Also, I need to define these two vectors. What are they? They are the two contributions to surface runoff. Remember ER1 and ER2. One corresponds to saturation of the basin. One is activated only when the catchment is completely saturated. The other one is effective up to saturation. And the vector is defined through a repetition of zeros for n delta t times. N delta t is the number of steps. Remember that I need to compute the river flow, and therefore I need to compute ER1 and ER2 at each time step. Okay. Now I am defining ER. ER will be the sum of ER1 and ER2. Remember that they are summed. And then I need to define the evapotranspiration. Again, a sequence of zeros for now. And then I am defining the vector of the river flow. Again, for now, a sequence of zeros. I want to save this page because I want to make a change in the program, which I'll make available to you in order to change the conversion factor as we will do. Okay, this is an interesting exercise. We spotted an inconsistency. Let's correct it and then modify the program. So let me save this page. Just 1 second. Okay, good. And let me work on the file rather than on the web page so we can make changes. Just let me make it, change the character because it's too small. Just 1 second because I don't remember how to change it. Let me see. Okay, here. Okay, let me go down. Okay. So what I did now, I saved it in a file so I can modify it. I suggest you to make the same so you can make changes, etc. Okay? Okay, now we need to start the computation at each time step. So first of all, this is Sk is the initial time step. Let's put it at 0. Or, sorry, 1. 0 is already computed. Q0 is 15. Okay. Now we can start a 4th cycle. Did we see already how to write 4 cycles in R? Yes, correct? Yes or yes? Okay, perfect. Because I'm teaching 2 courses, in both of them I'm teaching R, and therefore sometimes I make a bit of confusion. So here you see a 4th cycle that varies from Sk to n delta t. And the reason why we define here SK is that we want to have the opportunity to start the simulation from a subsequent time step. So not from 0, not from 1, but for instance from 4000 like it was before. In this case I set SK to 1, so we are starting from the first one. And then we open a second curly bracket because there is the sequence of instructions that is included in the fourth cycle. The fourth cycle is computed each time step. So it's computed 8,760 times. Now, to understand the sequence of instructions, it's a bit tricky. Now, remember that we defined W2, it was 0. Now we define W1. So at the beginning of the time step, remember, we just entered into the bracket, into the curly bracket. So we entered into the fourth cycle. It's repeated at each time step. So the first instruction is, of course, executed at the beginning of the time step. The other instructions in sequence allow us to reach the end of the time step. So we define W2 0, now we define W1. W1 is equal to W2. And let's understand this instruction because this is a key. What is W2? It's the volume at the end of the time step, which the beginning is defined to be 0. But after the first time step, W2 will be different from 0. And in the second time step, this instruction, by saying W1 is equivalent to W2, it says that at the beginning of the second time step, I am equating W to the value it had at the end of the previous time step. W is changing in time. I'm not using here a variable that changes in time because I don't need it. I am inside a loop that is repeated each time step. So what I do is to define a variable that is updated at each time step. I don't need to keep it. I just overwrite it each time. And to overwrite it each time, this is the key instruction. W1 is equivalent to W2. And W2 results from the previous step. I just want to check. Let's forget about the conversion factor, which still have to solve. Is it clear what we are doing apart from that? Okay. Okay. Now, keep in mind that explaining a code is by far the most difficult task for a teacher. And this is why I tell you, comment your code. Okay? Because by far, understanding a code, explaining a code, is one of the most difficult tasks that as engineer we are called to do. Okay? Now, I have to compute C1. What is C1? It's the value of CT at the beginning of the time step. Okay. How to compute C? Do you remember that we had an expression for C depending on W? I just try to show it to you. This is the expression for C. This one. This is the expression that we have to apply in that line, C depending on W. Let me go back to the code. Here it is. Do you recognize 1 divided by beta plus 1? And you can recognize everything. This is C1, which is computed on the value of W that we just defined. Okay, good. Now, be careful. do now, remember the definition of C. Now we have to add rainfall, because we are at the beginning of the time step. So let's add rainfall, okay? Okay, let's add rainfall. But we have to be careful. C cannot exceed the value of C max. By definition, cannot exceed it. Okay, so we cannot just add rainfall. If by adding rainfall we go over C max, C must be equated to C max. And this is the meaning of this instruction. I call it C2 because I added rainfall. So C2, it's the minimum between C1 plus P and C max. This means that if C1 plus P exceeds C max, the minimum is C max, C2 is equated to C max. Very simple. Now we can compute year 1. What is year 1? It is activated only when C exceeds C max. It is activated only when the catchment is completely saturated. So year 1 must be 0 when the catchment is not saturated. Okay, so let's compute it. ER1 is equal to the max between C1 plus P minus C max and 0. Okay, what is C1 plus P minus C max? Okay, C1 plus P is C2. I could have written there C2. No, not C2, because C2 is as an upper limit, sorry. C1 plus P is just C1 plus rainfall, and this can be greater than C max. If it is greater than C max, C2 is equated to C max, and if it is greater than C max, if I subtract from C1 plus P, I subtract C max, I have the exceedance if it is greater. If it is lower than C max, the result of this computation is negative. Okay, so if I take the max between the result of the computation and 0, I get 0 when C1 plus P is lower than C max. I get C1 plus P minus C max, which is the exceedance, when C1 plus P is greater than C max. So this is 0 until we reach saturation. Very good. Now we have to compute W2. W2, here it is. Basically, it's computed, let me go back to the web page with this expression. With this expression here, just look at this after the equal sign, this one. It is computed with this expression, but I need to use C2 because I am at the end of the time step, almost at the end. Okay? So you see here, there is C2, not C1. There is C2, which can be equivalent to C max if it is saturated. That's fine. Let's compute W2. And now there is ER2, computation of ER2. What is ER2? ER2, if you remember, let me go back to the web page. Let's look at the expression. Here is ER2. Is CT plus 1 minus CT minus WT plus 1 minus WT. Okay? If we look at the code, it is precisely that. It's, let's forget the max for now, is C2 minus C1 minus W2 minus W1. Remember that W2 I am at the end of the time step, so I am at the next already. W1 I am at the beginning of the time step. So this is the expression. And here there is a check. The check is the max instruction to make sure that the result of this is greater than 0. It shouldn't be needed because with the previous checks we shouldn't get any negative value from this computation. But it's better, you know, to make a check. To make sure that we don't get a negative value for runoff. Runoff is positively defined. So let's, when we know that a variable must be positive for sure, let's make checks. I don't think this is influential in the code because it shouldn't occur. But okay, and now we have ER1 and ER2. Now we have to compute evapotranspiration. So let me go back to the web page, evapotranspiration. Here it is. Remember this expression for actual evapotranspiration. It's what you find here. And now we have to update W2 by subtracting evapotranspiration. Very easy. W2 is equal to W2 minus E. Let's make sure that it doesn't become negative. W is positively defined, so let's put a max here. And now here we have the computation of ER. Now, let's make a question. What is the unit of ER that we obtained? Okay. What is the unit? The only external variable that entered this sequence of instructions from the curly bracket is P. It's rainfall. This means rainfall is expressed in millimeters per hour. So ER, which is a runoff, it's again in millimeters per hour. It's a runoff, so we are expecting something like volume divided by time. And if we get millimeters per hour, it's a length divided by time, so we need to obtain cubic meters per second, we need a conversion factor here. Okay, the same conversion factor that we defined above. But let's focus on it because we found a small inconsistency in the conversion factor. So let's make sure that we are aware of the unit here. It's millimeters per hour. Okay, good. Now we need to subdivide the runoff in two components through the parameter alpha. This is very easy. And U quick, it's runoff quick. The first component is just alpha times ER. U slow is 1 minus alpha. times ER. This is very easy. Okay. These two instructions refer to the reservoir, the only one. You remember that we have use law goes in the lower reservoir, the only one. U quick goes to the sequence of 3 reservoirs. Okay, so let's see what happens then. It happens that use law goes into the linear reservoir, the only one, and then we have to compute, we have to update the volume contained in the only one reservoir by adding use law. And then, after updating the volume, we need to compute the outflow from the unique reservoir. It's very simple in principle, because we need to keep the value, the previous value of W's law, and we computed it through the conversion factor at the beginning, which was conversion factor that we recognized was a bit probably too correct. Okay, and in fact you see here that W's law is updated. Is updated by adding to the previous value, which is here, use law. And this instruction could be given in a simpler way by adding simply to W's law, use law, but use law. It is computed in this way, again, because it was computed in this way in the original program. I decided to keep it. Okay, and then there is the computation of Q's law, which is derived from a similar expression. Now, here, let's move now to the sequence of the 3 reservoirs. You see here there is a 4th cycle, which means that we repeat 3 times the computation of the volume in the reservoir, 1 time per each reservoir. You can recognize here the same sequence of instructions that we had above. And which is repeated 3 times. Just let me check, because this is the first one. And this is the second one. For now, let's forget about, because I would like to explain to you why they are expressed in this way, to show you that it is equivalent to simply adding the contribution and then computing the discharge. Let's forget it for now, okay? Because if we have time at the end of the lecture, we will focus on this, and possibly we can modify it. Okay, and then we have the total flow. We just sum up, slow and quick. But at this time we need the conversion factor. Okay. So the conversion factor. Remember that we said that the conversion, the ER was in millimeters per hour, was computed here. This is in millimeters per hour. ER becomes, later on, becomes Q quick and Q slow. So they keep the same unit. So Q quick and Q slow are in millimeters per hour. So if we want to get Qt in cubic meters per second, what is the conversion factor? Okay. So if I work in millimeters per hour, so for instance, let's, how did I call it? Q? Qt. Up to now, the unit of Qt is millimeters per hour. Okay. So if I want to pass millimeters per hour, it's, so let's say cubic meters per second is equivalent to millimeters divided by hours times, okay, so first of all, we need to divide the millimeters by 1000, because we want to pass from millimeters to meters. Then we have to multiply it for the area of the basin in order to pass from millimeters to millimeters. We already passed to meters. We multiply by the area of the basin in square meters to get to cubic meters. Okay, so let me substitute this with this number. And then we have to divide by 3600 in order to pass from hours to seconds. So this should be our conversion factor. 1 divided by 1000 divided by 3600 multiplied times 12, 14, 6 zeros. Let's see if the conversion factor was computed in this way at the beginning of the program. Yes. Okay, so the conversion factor that we computed is correct for this computation. We still have to see if it is correct to apply it for computing W's law. Okay. Now the program is finished. Here there is instruction for drawing the plot, but let's forget it for now, because we already know how to draw the plot. Let's just focus on the last instruction, which is a return instruction. And what does it mean, a return instruction? When you put a return instruction into a function in R, it means that you are specifying what is the number, the result that the function should give back to you. So, because otherwise, every variable that is memorized